Alright, so as with any hypothesis test here, we're going to start out by writing our hypotheses. So our hypothesis test again is about whether there's a relationship between gender and having been in a fight among criminal justice students at Rutgers. Our null hypothesis then is that there is no relationship between these variables. So we can write that out in words, which is that there is no relationship between gender and fighting. Where fighting here means having been in a fight, but that's just a lot to write out. Our alternative hypothesis then is going to be the opposite of that, which is that there is a relationship between gender and having been in a fight. So we'll say there is a relationship So if we reject the null hypothesis, we'll be rejecting the idea that there is no relationship between gender and fighting. And we'll have evidence that points us in the direction of thinking that there is a relationship between gender and fighting. Step 2 is to calculate a test statistic. And like I said, the test statistic here you don't have to calculate. I'm just going to give it to you. In past years I have made everybody calculate this, and it's actually not that hard to do. It's just kind of long, and you know, like, you've got better things to do with your day. So you're off the hook here. I'm just going to give it to you. But what I do want to show you is what we do with this thing. So like in any other hypothesis test, we're placing our test statistic on a sampling distribution. The chi-square family of distributions, similar to the t-test, similar to the F distribution from the ANOVA test, it's a family of distributions that have different shapes for different configurations. In this case, the shapes are based on the number of cells you have in a table, as well as the sample size. But in general, they look like a right-skewed distribution like this. We're going to be placing our sample chi-square value on this distribution, where these are, possible chi-square values that could come from different samples, and these are the probabilities of getting each one. Chi-square, like F last week, is one of those that can't be negative, so your smallest possible value is 0. And we're just looking for values that are as large or for the probability of getting a chi-square statistic that's as large or larger than the one we actually got. So we're going to be placing our chi-square value from our sample on this distribution, and then calculating the area under the curve that's beyond that point to find our p-value. And then, as usual, we'll be using the p-value to decide whether to reject the null hypothesis or not. So in this particular case, the chi-square value for our test is 3.37. Again, without context, you don't really know if that's high or low, but what it's going to be used for is to calculate the p-value, which you can then interpret like any other p-value. So this tells us that on our distribution here, our sample chi-square value is at 3.37, and then our p-value is going to be the area under the curve that is beyond this value of 3.37. And again, how our test statistic lands on this sampling distribution, so this distribution of possible chi-square values you can get in a sample and the probability of getting each one, where it lands is going to tell you how likely or unlikely your sample results are in a world where the null hypothesis is true. So as usual, this is a sampling distribution if the null hypothesis is true. But since you're off the hook for calculating anything in this part, I'm just going to tell you that the value is 3.37, and we're going to use that to decide whether to reject the null hypothesis. So for a chi-square value of 3.37, you get a p-value of 0.066. So the area under the curve here is 0.066. And this tells us that if the null hypothesis is true, there would be a 6.6% chance that we would have gotten a sample chi-square statistic as large or larger than the one we actually got. So same interpretation as usual, and we're going to use it the same way. For this test, we'll say that our alpha value is 0.05. That's just the standard alpha level in the social sciences, so if it's ever not specified, we're just generally going to assume it's 0.05. And so at this level of significance, we're going to compare our p-value, which is 0.066, to our alpha level, which is 0.05. We're going to see that our p-value is larger than our alpha level. So here we fail to reject the null hypothesis. And in other words, the differences that we saw between what we would expect and what we actually got in our sample are not big enough to rule out the possibility that there's no relationship between gender and fighting in the population. One thing I do want to highlight here, though, this p-value of 0.066 is still relatively small. And so based on this hypothesis test, we can make the statement that, there's only a 6.6% chance we would have gotten our sample results if the null hypothesis were true. So it's still a pretty small chance. So when interpreting hypothesis testing and thinking about this, it's important to remember that the alpha level is sort of arbitrary, and it's set there as a threshold where we're deciding whether something's likely or unlikely. But it's important to kind of look at everything when thinking about, really how likely or unlikely your results are. So formally, at this alpha level, we fail to reject the null hypothesis. We don't have any evidence of a relationship between gender and having been in a fight. But we do have this relatively small p-value here. And so something that you'll probably see if you're reading papers for classes is sometimes they'll say, well, the results aren't significant, but p is equal to 0.06 or p is equal to 0.07. And what they're saying is that they don't have official evidence that something is the case, but they're noting that the sample results are still relatively unlikely. Alright, so that's it for the hypothesis test. So I'm going to go back into the PowerPoint, show you a hypothesis test in Stata, and then talk about correlations for a bit.